Hello. In this video, we're going to continue with Lab 3, and I wanted to go over the operation of measuring common mode rejection ratio in LT Spice. So the measurement of common mode rejection ratio is your amplifier's ability to reject noise. So an ideal amplifier connected in normal operation, you should get a very high gain. That's dependent on your feedback network. And then in common mode, which common mode is when both inputs are connected to the signal. Ideally, an amplifier would see 0 on the output because they're going to cancel each other out. But what you'll see experimentally is that there will be some sinusoid there, and the common mode rejection ratio is how well does an amplifier reject that noise. So this is going to help with this last part of the lab where you want to compare the BJT op amp from lab 2 with your MOSFET op amp from lab 3. We went over all these other parameters in previous labs, so if you need help, refer to the previous labs. Okay, I wanted to point out that I'm using for the reference resistor 10K, so that should give me a total current of approximately 1 milliamp. So the first step that we're going to do is just measure the input. Let's measure the input first. So I know that my input should be 200 millivolts peak to peak, but you can see that it gets slightly attenuated. So if you want really accurate results in LT Spice, be sure to measure your input signal as well. And I'm just moving over the decimal. And now we're going to take the measurement of the output. And the output we're going to call 1.98. And if you want to use all significant figures, that'll give you a more accurate result also. So our differential gain in normal mode is 9.91 volts. So now we want to measure common mode gain. So to set up common mode gain, or set up your amplifier in common mode, what you're going to want to do is take these negative nodes out of the circuit and create another positive node. So now the feedback network is still connected and the input signal is going to both inputs. Okay, now we're going to run it and measure the output. You can see there's a little bit of DC in our signal, but we are primarily concerned with the sinusoid. So we got 34.3 and microvolts. So e to the negative 6. So our common mode gain is 171.6 microvolts. And I'm looking at this value here. You can ignore these values. These were results from previous labs, my previous lab when I took the course, and I just want to show you how, the difference between 9.9 and 9.7, although it seems like a lot, once we get to common mode rejection ratio in decibels, it's not going to be a very significant difference. Okay, so now we're doing common mode rejection ratio linear. So I have it set up here to take the absolute value of J6, which is the differential gain, divided by the common mode gain, which is J11, and it gives us 57,759, and then we want to turn it into decibels, so 20 times log common mode rejection ratio linear value, and do the calculation, and it's 95.23 dBs. So you can see, even though these values were different, the common mode rejection ratio, wasn't significantly different. So one thing I wanted to point out, in the last lab, I was talking about changing the total current, increasing the total current, so your linear range is longer. You are stretching out that linear range to be able to drive a heavier load. So I wanted to show you that by increasing the total current, you can actually get a much smaller noise on the output. So we can see here this is 4.7 microvolts, and all I did again was change the reference resistor to 100, which increases the total current to about 100. We're getting 95 milliamps, but approximately 100. And what was it? 4.7 microvolts. So we plug that value in for the common mode output, and you can see how big of a difference that makes. So now our common mode rejection ratio is 112.5 dBs, which is much better than when we were using only 1 milliamp. So I just kind of wanted to point that out. And the last thing I wanted to go over, now that we're done with the common mode rejection ratio, is the phase margin. So the phase margin is the measurement of the stability of a system. So to increase the stability of an amplifier, you should increase the phase margin. And what we're going to do is look at the Bode plot, and we're going to do that through the AC analysis. But before I do that, I need to set the amplifier back up into normal operation. So putting these connecting the negative terminals back up. I'm going to rem the transient analysis out, and then I'm going to unrem the AC analysis. Okay, so we're doing the AC analysis. I'm going to change it blue so it's a little easier to see. And what you're going to want to do is just get one cursor, and we're going to check the magnitude. When the magnitude's 0 or gets really close to 0, we're not going to be able to actually get this value to be 0. I wonder if we can just, yeah, no, you can't get it to be 0, but we can get it close and we can see what the phase is, and that's going to be our phase margin value. So you can get it close and then use your arrow keys to really like dial it in. So, 581 micro dBs is practically 0, and we're getting negative 19.89, a phase of negative 19.89 degrees. So that would be our phase margin for this circuit. And again, I wanted to point out that by increasing the total current and extending that linear region, which I talked about in the previous video, and then we'll remeasure it right now and see what we're going to get. So 127 micro dBs is practically 0, and we're getting negative 8.9 degrees. So that increased the phase margin. We were at negative 19, and we increased it to negative 8.7 degrees. So again, by increasing the total current, we're able to create a more stable amplifier. So this phase margin wasn't really part of the assignment for the lab, but if you do take screenshots of it or are interested in it, go ahead and take some screenshots and put it in a slide in your report and talk about it, and I hope this video helps. Thank you.